time or so. Thank you. In 2009, I moved from industry to academia, and shortly thereafter, someone said, I was working on CCS, give us a passive continuous monitoring process, if you would. That led by a strange series of turns to particle physics, the outer reaches of the universe, railway tunnels, back to CCS, and with the help of Gareth 6 months ago, to explore the possibility of doing some of the applications of Muon tomography within mine water developments. Now, when it was first suggested to me to use muons, I sort of said, good idea, and then dashed home to find out what the devil they were, somewhere in the back of my mind. So muons are subatomic particles. They sit in the same class as electrons, but are a wee bit heavier, about 200 times, and they're created in the upper atmosphere when cosmic rays from distant supernova bump into oxygen and nitrogen atoms. And those cosmic rays, traveling at nearly the speed of light, suffer time dilation and whiz down through us. So the area of your fingernail, one goes through there every minute or so. And they're attenuated by density and thickness. So if the dynamic Earth had a lead roof on top, we would be wearing or using an umbrella. We would have fewer muons go through us than otherwise might be the case. And because of that, they've been used in a number of applications. First of all, tunnels in Australia were deploying them. More famously, they've been used to detect hidden chambers, or in the case of the pyramid that was chosen, non-chambers, and even the geometry and evolution of magma chambers in Japanese volcanoes. So they effectively are like X-rays, but far more penetrative. They've been recorded down deep mines of 3 and 4 kilometres, albeit at a much lower flux than we get here on the surface of the Earth. And the reason air crews have to have the screening each year to make sure they've not been irradiated is because of the muon flux that much higher. So the bottom line there is essentially the 1 centimetre square and 1 minute. The muons are attenuated by thick rock, dense material. And so what we tend to do is think of things in a water equivalent. And it's very, very simple. So quartz has a density of 2.7. So effectively, relative to water, the attenuation rate goes up by a factor of 2.7. That allows us to monitor or measure the density heterogeneity above a detector. Now, when we first started on this for CCS, with depths of 2 kilometres down boreholes, speaking to the particle physicists, they said, well, for a detector, we would probably use a cloud chamber about the size of this coffee table, and we'd need to cool it to liquid nitrogen temperatures. And that left us scratching our heads for a little while, but some of my very smart colleagues instead started to suggest we worked with these scintillating materials. So when a muon hits this scintillating material, it creates a photon or several photons. And if you look at the bottom right-hand corner with the rod, a photon or 2 photons in that. Oh dear. Oh, it's come back. That could have been caused by a muon flux. Anyway, bottom right-hand corner, a rod, photons to either end, and we measure their arrival times. If you stack a bunch of those rods together, if the muon goes through several, you can plot its path. And if you can plot its path and its intensity, and we know huge amounts about muons because they get in the way of all those experiments to look for dark matter, this mode is not appropriate. Oh dear. It doesn't show on yours. There's a sign on there saying it's not appropriate. Anyway, in 2015, we developed a tool for monitoring CO2. We deployed it down Bulby Mine in Yorkshire and started to measure muons down there. The rug was pulled from CCS in 2015 by George Osborne, and we were left with the technology and nowhere to play with it. The opportunity arose in 2018 when we were invited to monitor or measure the occurrence of old shafts or shafts in an old Victorian railway tunnel. That's shown on the bottom. Now, clearly you can see the shafts, but we took our truck along and we measured. Gone again. What's going on? Clearly someone stopped shining on me. Along the tunnel, and we could see a number of anomalies which defied our modelling. And you can see those as the little peaks on the left-hand chart and then rather zoomed in on the right-hand chart. What we did find is at the north end of the tunnel, we found a Muon peak, and yet there were bricks above us. And my colleagues went to the Network Rail and said, we think there might be a hidden shaft at the north end of the tunnel. And they went, yes, there is. We just didn't tell you about that one. And so what we were able to do is see beyond the bricks. Now, normally in railways, you bash the roof and hope it doesn't fall on you and listen for a sonorous sound. This is a passive, non-destructive technique. And you can see how we've refined it in the bottom right-hand corner. We're able to monitor not just the occurrence of shafts, but also cut and fill. So, back to CCS. And working first of all with CGG and then with ADNOC, we have developed and tested in the test site in Norway an ability to monitor CO2 as it's injected into a subsurface reservoir. Admittedly quite shallow and gas phase, but that allows our experiments to actually be conducted quite quickly. And it was with this a few months ago, maybe 6 months ago, Gareth Farr from the Coal Authority said, can you not give us something on the application for mines? And we scratched our chin a little bit, and with Gareth's help and with the Gateshead project, we did just that. So what we've done is simply some modelling. And what we do always is model the flux of muons and their attenuation before we go and measure it. So there's the mine, one of the intervals in Gateshead, and you'll see about 2/3 of the way down, the high main, that's the interval that's been mined out and one of the intervals from which water is being withdrawn. So we model that, as you can see on this simulation, in 3 dimensions. The different colours are different densities of the rocks therein. And the bottom one just shows the 3-dimensional piece. And we put in that a shaft, and within the shaft, or the borehole rather, a detector. Some 70 metres long, which we wouldn't do in real life, but we segmented that so that we could look at the muon flux that would come through both above, within, and beneath the mined layer. And in doing that, now this is where I fall off the cliff of knowledge, so you'll have to excuse me. What we're looking at are areas under curves, and for what I'm told is a receiver-operator characteristic. Now, this is something which both particle physicists and I understand machine learning folk use to look at the relationship between a random event and something which perturbs you away from random. So on this plot on the left-hand side, the black line which joins the bottom left and the top right-hand corner is, if you like, randomness. And the deviation away from randomness shows how the level of detection. And what we find for this won't come as a surprise. It might come as a surprise to particle physicists, but it won't come as a surprise to anybody in this audience that when we put the detector above the coal seam, we don't see it very well. When we put it, it's a bit like Goldilocks on the 3 Bears, really. When we put it deep beneath the coal seam, we don't seem to pick it up too well. But when it's just beneath the mined out coal seam, we can very easily differentiate between a mined zone and an unmined zone away from the point of detection. What we're seeing is typically a cone of around about 120 degrees in conical, whatever it's called, conical angle away from the detector point. And so not only can you, clearly you've drilled through it, so you know if your drill bit drops off the end of the plate, you've gone through a mine zone, but we can see away from that. So there is a real possibility that as we continue to develop the system here, that we will be able to reduce the uncertainty associated with drilling wells. I can't remember how many Gateshead drilled, it was a couple of dozen maybe, and identify areas close to or within the range of the detectors, but away from the borehole, where we're more likely to find void space than we are rock. In other words, improve the chance of success of the wells. So, very, very early days, but the initial results, as you saw, are really quite promising. And we think in many instances we may be able to identify missing coal seams away from the well as drilled, and therefore improve performance in drilling the next one. Thank you.